Okay, so this is where we ended last class, talking about just gases MCQ. We did an ice chart with it and treated it like a limiting reactant problem. So right now we're going to talk about this concept of root mean square, and I don't necessarily need you to know the root mean square concept. I just want you specifically to know that this guy right here, this mu RMS means speed. It's pretty much saying how fast and for this chapter we're talking about gases, do gases travel, and how fast they travel is equal to 3. R is the gas law constant. Now, it is specifically the 8.314 constant, and we'll talk about this in a second. T is temperature in Kelvin, and big M stands for molar mass. So pretty much the speed of any gas depends on its temperature, what temperature it's at, and how heavy or light it is, its molar mass. Now, on your equation sheet, the 8.314 is written like this. Now, what's interesting, and I don't need you to know this, this equation right here is no longer on your equation sheet, meaning the AP test will not have you do calculations. If I have you do calculations on a test, I'll give you the equation. We're going to do calculations with it and then discuss it conceptually, because conceptually is totally fair game. They're just not going to make you do calculations with it. So I know you don't know this, but I'm going to tell you a joule is the same thing as a kilogram meter squared over second squared. So what they've done is they've taken this whole term and plugged it in right here, and that's where they get this kilogram meter squared per second squared over mole Kelvin. Okay, so again, this is not on your equation sheet. You do have to be careful of a few things. Again, like usual in this chapter, temperature needs to be in Kelvin. And then you got to be careful with the molar mass. Because of this kilogram right here, we're going to have, right, we usually do molar mass as grams per mole. And if we want the units to match, we're going to have to do it as kilograms per mole. So that's something weird we've never really done before. But again, we're calculating the speed of how fast or slow gases move is the whole point of this. So let's look at the first question. So 1 and 2 are no longer fair game on the AP test. However, number 3 is. So I'm going to do the math to prove to you number 3, and then we'll talk about number 3. So it says determine the root mean square, which means the speed or the velocity of the following gases at 25 Celsius and include units. So we're going to do it for helium, and then we're going to do it for oxygen. So helium, speed, root mean square equals 3RT over molar mass. So square root of 3. Now the R is the gas law constant. And then I'll write all those crazy units. So that's the R. And then T is temperature in Kelvin, so that's 298 Kelvin. All divided by molar mass. Now, helium is 4 grams per mole. So we have to do it in kilograms because this R constant has kilograms in it, 0.004 kilograms per mole. So now what's interesting is if we look at the units, kilograms cancel, moles cancel, Kelvin cancel, and we're left with meters squared over second squared. Well, you're going to square root that, so your units are going to be meters per second. So I'm going to give you a second. I want you to plug all this in your calculator, and then I want you to square root, and then let me know when you have an answer. You need to be good at practicing with your calculator, please. So this is the number you should get with 3 sig figs. So now we're going to do this with oxygen. Now remember, oxygen is O2, right? So for oxygen, here we go. The root mean square, or the speed, or the velocity, however you want to look at it, is the square root 3 times the R constant, which is the gas law constant. And then it has all these crazy units, kilogram, meters squared, all over second squared, and mole, and Kelvin. And then times temperature. Now the temperature is the same for both gases, so 298 Kelvin. All divided by molar mass. Now O2 is oxygen gas, and it's 32 grams per mole. So that's 0.032 kilograms per mole. So let's look at the units again. Kilograms, cancel, mole, cancel, Kelvin, cancel, and you're left with meters squared over seconds squared. And then you're going to square root it, so you'll be left with meters per second. I'm going to give you a second to calculate this. All right, does anyone have a number that you're willing to share by unmuting yourself? When I go back to the chat, it messes with my recording. It's a smaller number. I don't remember from last class what it was. Anybody? 481? Okay, so let's see. 3 sig fig, so we'll call this 482. 482 meters per second. So here's the concept. At the same temperature, both of these were at 25 Celsius or 298 Kelvin, at the same temperature, lighter gases move faster than heavier gases. Helium is only 4 grams per mole. Oxygen is 32. Oxygen's heavier, it has more weight to pull, so it moves slower than helium. Lighter gases move faster, heavier gases move slower. That is the point of this conceptually. So the next question asks you to do oxygen, but they want you to do oxygen again, but at a different temperature. And they wanted you to do it at 50 degrees Celsius. So you just plug back in and let's compare. So this one was comparing size. Now we're going to compare temperature. So we're going to do O2, but we're going to do its speed at 50 degrees Celsius. So again, the 3 and the R are the same. So it's 3 times 8.314 times, the temperature is now 50, which is 323 Kelvin. And then the molar mass is the same because it's still oxygen, so 32 grams per mole. So let's calculate this one out. What do you get for the speed of oxygen? So this is oxygen at 25 Celsius, and then this is oxygen at 50 Celsius. And let's look at their speeds mathematically. All right, so we get 502 meters per second. So mathematically, this shows at 50 degrees Celsius, oxygen moves faster than it does at 25 degrees Celsius. So hopefully, conceptually, this makes sense that if you heat gases up, they move faster. Or if you heat any particles up, they move faster. So at higher temperatures, gases will move at higher speeds, higher velocities. Okay. So this concept, I'm not going to read to you the slide. You guys can read this on your own. I'm going to more talk about the slides. But the concept is that even though gases like in your room right now all have about the same, they're all at the same temperature, they're technically not all moving at the same exact speed. Some of them are moving a little slow. Some of them are moving really fast. But on average, they're moving around the same speed. So we generally talk about this as like a distribution or on average, okay? So this Maxwell-Boltzmann distribution curve, the whole point of this is this idea that the area under the curve is the total number of molecules we're focusing on, and that at any given moment, some molecules are moving slower, small amounts of molecules are moving faster, but a huge portion of them under this curve are moving about the same speed, okay? But they're not all exactly the same, even if they're under the same temperature. So notice that the graph is not perfectly symmetrical. So like this is a curve, right? And it has like a tail at this end. So it's not a perfectly symmetrical curve. And then again, this area under the curve represents all particles, all of the particles being inspected or discussed, okay? And the graph ends at 0, right? Because you can't have negative speed. So what's interesting, and I don't need you to necessarily memorize this or anything, but the most probable speed is going to happen at the peak. You have the most particles under here. So if you go like this, right? This is where you're seeing the most, this is the area under the curve, the most particles are at the tip of the curve. Now, what's interesting is the V average. The average speed is slightly off of the tip of the peak of the curve, and the reason that is because my curve is not symmetrical, and there's a little bit extra area over here, so it's actually shifted a little bit to be the average, not perfectly at the peak. Now, if this was a perfectly symmetrical curve, the most probable speed and the average speed would be the same thing, but because the curve is not symmetrical and has a little extra area around here, the average is slightly shifted. Okay, so let's look at this. So this is showing the speed of gas molecules, and then the number of molecules is what's represented by all the area under the curve. Now these are supposed to signify the same amount of molecules. The number of molecules in the blue curve is the same as the green curve and is the same as the red curve. So you go, well, how is that? Well, yes, the blue curve is taller, but it's also more narrow. So while the green curve drops down in height, it also makes up for it by getting wider. And then the same with the hot gas. The hot gas is the shortest one, but it's very, very wide. So the areas under all of these are considered to be the same for this example. Okay, so what's the point of this? The whole point of this is that this is showing that hot gas molecules, more of them move faster than cold gas molecules. You have more cold gas molecules moving slower. So let's draw on here. Let's compare the room temperature and the hot gas. So let's look at where they overlap, which is right here. So the area under the curve for the red guy is this. All of this area is red. So a lot of molecules moving at fairly high speeds. Now, the green is also right here, but it cuts off here. So the area under the green is only this much. This is less molecules moving as fast. And there's not as many molecules moving as fast because they're not as hot, which is this whole concept. So look at the blue one doesn't even have molecules that are moving at the same speed as the hot gas. You have more molecules for the blue, a lot of molecules under here that are moving at fairly low speeds, right? This would be a low speed and this would be a high speed, okay? Because we know that colder gas molecules move slower. That's all this is showing to you. Okay, so again, same concept. You have a gas, and you have the gas at two different temperatures. One of the temperatures is 100, and another temperature is 0. So you focus on the area under the curve. So look at the red. This is where they overlap right here. All under here is how many molecules are moving at whatever this speed is and higher. Okay? If you look at the blue part where they overlap, the area under the blue curve, oops, sorry, I didn't draw that very well, is definitely smaller, which means less particles are moving as fast. That's because they're colder. Colder particles move slower than warmer particles. Okay, so you have this distribution curve. This is your initial curve. And you impose the second curve on it. So let's talk about all things that will apply. Is the peak height of the graph of number of molecules versus speed get shorter? Is that true? Does the peak go from 1 to 2, does it get shorter? Yes, it does. Okay. The average molecular speed of the gas decreases. Is the speed decreasing? Yep. Okay, look at the curve shifted from 1 to 2. My speed is definitely slowing down. The graph of number of molecules versus speed becomes more narrow. Yes, that is true. Now, here's the difference in this one. The area under curve 2 is not the same under curve 1. If you wanted it to be the same, when you shifted it to make it more narrow, you should have also made it taller, okay? So right now we're not considering similar areas, all right, under the curve. The root mean square, which means the speed of the gas increases. Well, no, from 1 to 2, obviously the speed dropped, so this would not be true. Okay? So now, This chart is focusing on different gases so that we're not changing temperature. We're going to assume all at the same temperature, so same temperature. And what they're doing is they're just changing the identity of the gases. Now again, notice that the curves are going to be considered to be the same number of molecules. This is taller, but it's narrow. This is really short, but it's also really wide. So all the same number of molecules, okay? Because the areas under the curve are all considered to be the same. So the only thing that's changing is the identity of them. So hydrogen is 2.02 grams per mole, helium is 4, water's 18-ish, nitrogen's 28, and oxygen is 32. So what is the point of this? So look at where hydrogen and helium overlap. Hydrogen has more molecules moving at higher speeds than helium does. Helium doesn't have as many. Helium's area under its curve is right here. Why? Why is this? Why does hydrogen have more molecules moving faster than helium? And why does oxygen have the most molecules moving the slowest? Lighter mass, very good. So the lighter gases move faster, heavier gases move slower. That's all this is showing. Okay? All right. So diffusion is spontaneous mixing. It's probably a word you've heard before, of any particles, and in this chapter we're talking about gases, caused by the fact that they tend to just move randomly. So small particles diffuse faster than heavier particles because they're lighter. Okay? Now effusion is kind of a new concept that you've likely not heard of before, and this is gas particles trying to escape something, or diffuse or effuse, but they're trying to make it out of a small opening. So a great example of this would be a tire. So a tire that has like a hole in it. If you have a tire that has a hole in it, the air will try to eventually get through the hole, and then your tire goes flat. So that tiny opening is the hole, and the gas try to escape it, is an example of effusion. Now, smaller masses effuse faster. If they are smaller, they can fit through the opening easier. They also move faster if they're smaller. So if they move faster, they have a better chance of reaching the opening and escaping. Now, so this is also affected by temperature, right? So like on a hot day, your tire will go flat quicker because the gas molecules are moving faster on a hot day, and if they're moving faster, they have a better chance of escaping, which means on a cooler day, your tire will go flat a lot slower because the gas molecules aren't escaping as quickly. They don't have the ability to escape as quickly. Visually, the difference can be shown like this. So you have a container, it has a barrier in it, you remove it on their own. The gas molecules aren't just going to stay on their own side. They'll mix evenly and diffuse, okay? And then effusion are the gas molecules trying to fit through a small opening. So this is the difference between diffusion and effusion. Now, this is called Graham's law of effusion. However, you can still use diffusion, okay, in this law. All right. So remember that, so rate is like some sort of unit over time. So like the rate at which you drive in America is measured in miles per hour. So that's like also known as speed. So rate can also be called speed. Speed is a type of rate. Speed or velocity, they're all interchangeable with the words rate. Okay, so this is like the speed of one gas compared to the speed of another gas, and it equals the square root, and then notice their molar masses switch spots. Okay, so like the molar mass of B goes up top and the molar mass of A goes on the bottom. So all this is saying is the speed at which gases move, assuming temperature is the same, depends on their molar masses. Okay, lighter gases move faster and slower gases or heavier gases move slower. So you go, okay, I don't need you to know this part per se, but where did this come from? Like, where did they just pull this equation out of? Well, they didn't just pull it out of nowhere, right? We know that speed, which is a rate, Okay, this is spade. Or root means square, whatever. That's speed, right? The fancy word for speed. And we'll do gas A equals, we just did this at the beginning of class, 3RT over big M, and that would be of A. Well, if we're going to compare the speed of one gas to the speed of another, so I would divide this by the speed of some other gas, B, well, that would equal, so I have to divide, the square root of 3RT over the molar mass of B. Well, what happens? Well, the 3RT cancel, right? This flips up, and that is how they got this equation. The rate or speed of one gas relative to the rate of another gas is the inverse square root of their molar masses. They derived it from the speed equation. They didn't just like pull it out of nowhere. So that's how that's how Graham's law was determined. So let's do some practice problems. Calculate the ratio of the effusion rates of hydrogen gas and uranium hexafluoride. So, okay, the ratio of rates of effusion. So let's look at this. We're going to talk about the rate or speed of hydrogen gas relative to the rate or speed of uranium hexafluoride. So they want you to calculate the ratio of effusion rates. That's this entire thing. This is a ratio of rates. So I just plug in square root. Uranium hexafluoride goes up there. Hydrogen goes here. I think uranium hexafluoride is 352 something. Oops, whoa. Let me double check. And then hydrogen is 2.02. Oops, 2.02 grams per mole. Let me double check the uranium hexafluoride. 352.02 divided by 2.02, and do not forget to square root it. And so you will get 13.2 over 1. What does that mean? Hydrogen, the rate of hydrogen or the speed of hydrogen, hydrogen effuses or diffuses 13.2 times faster than uranium hexafluoride because it is so much lighter. Lighter gases move easier. This guy has a lot of weight to lug around. So it effuses or diffuses much, much slower. Questions on this? So let's do another practice then. The molar mass of helium is 4 grams per mole, and the molar mass of air. Now, air is a combination of multiple gases, so you can't just go like look up air on the periodic table. So I gave you air's approximate molar mass. What is the ratio of their diffusion rates? Well, this is Graham's law. So the rate or speed of helium relative to the, sorry, that's HE, relative to the rate of air. So this is a ratio of their rates. This whole thing right here is what this is, equals the square root of air goes on top, helium goes on the bottom. So 29 divided by 4, and then don't forget to square root. So 2.69 over 1. What does that mean? Helium diffuses or effuses 2.69 times faster than air because it is lighter than air, so it can move more quickly. Questions? Okay, this one's a little bit trickier. So let's talk about some wording. You know the College Board loves using like really, really fancy wording, and it's not to trick you because this really isn't that hard to understand. But it says an unknown gas composed of homonuclear diatomic molecules. Well, what does homo mean? It means same. Nuclear means nucleus. Well, an element that has the same nucleus as another element is the same element. So they're literally, all this fancy wording is telling you that it's going to be a diatomic. It's a diatomic. So let's refresh on who our diatomics are. H2, N2, O2, F2, Cl2, Br2, I2, At2 isn't really, but if you want to put that, that's fine. Oops, I forgot bromine. Okay. And why homonuclear? Well, because it's a hydrogen attached to a hydrogen. They have the same element. It's two of the same elements attached to each other. Homonuclear, same element. That's all that that's saying. Okay. And they say that the rate of the unknown diatomic, just call it X or X2, whatever, is 0.355 times the rate of O2. And if you think about this conceptually, the rate of the diatomic is a fraction of the rate of O2, meaning this diatomic is heavier than O2. Okay, if this would have said the rate of this diatomic, this unknown diatomic, was 5 times the rate of O2, that would mean this guy is moving 5 times faster than O2. But because it's a decimal, we know that it's moving at a fraction of the rate of O2, which means it's not moving as fast as O2. So it's going to be heavier than O2. So how do you do this? Well, this doesn't look like Graham's law right now. And we know Graham's law involves rates and molar masses. So I'm going to rearrange it to make it look like Graham's law. I'm going to compare their ratios. The rate of the unknown diatomic compared to the rate of oxygen gas. So again, I got rid of this. So this guy's number, so before we were solving for this, now we know this. It's this number. So this number equals the molar mass of O2 goes on top, which is 32, right? This guy goes up here, and this guy comes down here, and we don't know the other guy's molar mass. So how do you solve? Well, you square both sides. So 0.355, squared equals 32 over big M. Now you've got to get the big M up top, so you multiply both sides by capital M. That gets rid of it over here. And now you've got to isolate the big M, so you divide both sides by 0.355 squared. So this is 32 divided by 0.355 squared. Okay, and you calculate it out and you get 254 grams per mole. So now there's two ways to do this. Because it's two of the same element, you can just take this number and divide by 2 and go on your periodic table and go, okay, well, who's close to 127? Because 254 divided by 2 is 127. Well, that's going to be iodine. So iodine and iodine, I2, is your diatomic. 127 plus 127 is 254. I2 is your diatomic. Any questions? Okay. All right. Conceptually, you can take this, we used to actually do this in class. I used a straw, but you can use like a glass tube. You take super duper duper concentrated HCl, and it's so concentrated, I think it's like 12 molar. It's so concentrated that HCl vapor gas comes off of it. That's how concentrated the liquid is. And then you do the same with ammonia. You take super duper concentrated liquid ammonia, and it's so concentrated that ammonia vapor, like it looks like it's steaming in essence. They both look like they're steaming, but it's really the HCl liquid turning into HCl vapor gas, and same with the ammonia. And you put them in the ends of the, so you soak them, and then you put them in something that's sealed, like we used a straw, or you could use like a glass container, glass tube, to kind of try to trap the gas. And the reason that you try to do that, or the gases, because when ammonia comes into contact with HCl, it makes ammonium chloride, and ammonium chloride appears as this like kind of like white ring in the tube. So you pretty much notice it when you see this. You know that these two guys have finally run into each other because now you've produced this. So the question is where on this tube, based on these letters, are you going to find them run into each other? I would like everybody to answer, please. You can answer on the chat. Where are you going to see the ring form, the ammonium chloride form, on here based on these two gases? A, B, C, or D, and then you want to explain why will you see it where you've chosen. So again, they meet at A, right, because the ammonia moves faster because it's lighter. So if they're meeting at B, the chances that, you can kind of like make an assumption that both of the gases are similar. They don't have to be identical, but pretty similar in molar mass. So if they travel about the same speed, they'll meet in the middle. If they were meeting at C, it was because the gas over here was lighter and was able to travel farther. Meaning I could like switch these. I could put the HCl over on the right and the ammonia over here, and that's where you would have picked C because you just changed the locations of both substances. Very, very good. It seems like you guys understand this concept pretty well. Okay. So on this part, so right, we're talking about gases moving and their speed. So in physics, average kinetic energy or kinetic energy is measured like this. You're never going to use this equation this year. I'm just going to talk about it conceptually, okay? So here's why. So average kinetic energy equals their mass and their U, that's speed. So here's how you have to think about it. If a gas is light, it has a low mass, right? But if it's light, it moves faster, right? But if a gas is heavy, its mass is higher, but it moves slower. Okay, so they change relative to one another. So really, for the sake of this class, we're not going to look at this. We are going to say all gases have the same, on average, kinetic energy if they are at the same temperature. I don't care who the gas is. Helium gas and uranium hexafluoride. If they are both at 25 Celsius, they both have the same average kinetic energy. Well, you go, but how is that possible? Because the helium's lighter. Well, yeah, its mass is smaller, but that means it moves faster. And you go, well, how's that possible though? Uranium's heavier. Well, yeah, its mass is bigger, but it moves slower. Okay, so if they're at the same temperature, on average, they have the same amount of energy. Okay, on average. So let's apply that conceptually. You take oxygen gas at STP. So remember, STP is 0 Celsius, 1 atmosphere. And they compress it, meaning they're shrinking the container. They're making the container smaller. They're decreasing volume at a constant temperature. So they're not allowing temperature to change. What effect does this have on the average kinetic energy of the oxygen gas? So it should have no effect on the average kinetic energy because you're not changing temperature. So A is no effect because temperature is not changing. Temperature is staying constant. What will shrinking the container do to the speed of the oxygen molecules? Well, if the temperature is not changing and the gas isn't changing who it is, there will be no effect on the speed of how fast the gas molecules move. Now, what will happen to the total number of collisions of oxygen gas molecules with the container walls? Well, if you shrink the container, the oxygen gas is going to hit the walls more often, aka pressure is going to increase if you drop it, because there's less space for the gas to move around in, so it will hit the walls more often. So that's the only one that changes as long as temperature remains constant. Okay. All right. So, kids often have trouble remembering this. I'm going to do my best to try to tell you ways or tricks to remember this. So this whole entire chapter, we've pretended that gases behave ideally. They follow our kinetic molecular theory, which is a bunch of assumptions that we make, some of which are good assumptions, some are not so good. But it allows us to use this, the ideal gas law, to do calculations, which, if you remember, isn't too awful, right? You just plug numbers in and you can solve for pressure or volume or moles or T or whatever, okay? So the real gases, though, really only behave ideally under certain conditions. And they are the most ideal when they're not under a lot of pressure, okay? So like you, think about you, like you behave better or you feel better when you're not under a ton of pressure, low pressure, and higher temperatures. So lower pressures and higher temperatures is the most ideal, which means the least ideal would be when you're under a ton of pressure, or when the gases are under a ton of pressure and they're not really, and they're not under a ton of, lower temperatures, and they're at lower temperatures. So ignoring pressure and temperature and looking at just identity, the best ideal gases are all of our noble gases and our diatomics. Of all gases, your noble gases and your diatomic gases behave the most ideally, okay? Now, when you start messing with their pressure and temperature, they can start to do what's called deviate from ideal temperature, or from ideal conditions. So the word deviate means to move away from. So if you're starting to deviate from ideal behavior, you are becoming less and less ideal, aka not ideal. And when you're less and less ideal, Pervnert gives you, if you're trying to do calculations, not as good of results, okay? Here's the thing. When you start throwing gases under tremendous amounts of pressure, usually by shrinking the volume of the container, all of a sudden, the size, right? We pretended in the kinetic molecular theory that the gas size is negligible. That allows us to use Pervnert. Okay, so and if you're in a really big container, so big volume, which would mean low pressure, right? Low pressure, the gas molecules barely make up. Most of the container is empty space, and only a tiny bit of it is gas molecules. So this is good. This holds true as long as you're not under a tremendous amount of pressure. However, if you shrink the container, aka increase the pressure drastically, the gas molecules make up most of the container. So now their size is no longer insignificant. So it will affect the total pressure, okay? And the total volume. We can't just say that they don't take up any volume anymore, because now they're in such a small space that their volume starts to become significant. So Pervnert would kind of be out the door. So we pretend all these things to make our life easier, okay? And then let's talk about temperature. If you heat gases up really, really hot, they move really, really fast. If they move really, really fast, they zip by each other. They don't pay attention to each other. They hit the walls of the container, they bounce off, and they keep going. Now, when you cool them down at lower temperatures, they move slower. And if they move slower, they have a chance to recognize other gas molecules. And then what happens is those gas molecules can attract or repel each other, and they'll notice each other, and that will affect how often they hit the walls of the container, because instead of zipping past each other, they're now interacting with each other instead of running into the walls of the container. So when you cool them down, that really messes up this theory that gases aren't attracted or repelled by each other, because when you cool them down, they have more of an opportunity to interact with one another, okay? So this chart is just showing you, the whole point of this is that the closer you are to this line, the more ideal you are, okay? And we're going to focus on pressure. Well, we know gases behave most ideally at lower pressures, okay? So let's look. You have three gases. The lower the pressure, which is down here, the lower the pressure, the closer these guys are to the ideal line. as we start to increase pressure, these gases start to deviate or move away from this ideal line. Now notice who stays closest to it. Who's the closest to ideal even at higher pressures? And why? Well, it's helium, and it's because I told you your noble gases are some, besides diatomics, as ideal as it gets. So even under higher pressures, yes, it's deviating from ideal, but it's the most ideal between these three, and that's because of identity, because it's a noble gas, and noble gases tend to behave fairly ideally. Even at crazy high pressures, they still are closer to ideal than the other two gases are. Okay? Now, if you look at this, this is just one gas. This is nitrogen gas. So this is the concept of temperature. So nitrogen gas at 1,000 Kelvin, nitrogen gas at 500, nitrogen gas at 200. Nitrogen gas at 1,000 Kelvin, look how ideal it is at low pressures and high temperatures. Okay? And then as the pressure gets bigger, it starts to stray from ideal or deviate from ideal. But compared to these other lower temperature, even at low pressures, if you have low temperature, these gases are deviating from ideal behavior. Ideal is low pressure, high temperature. That's the best conditions you can get. So these, even though these are under low pressures down here, they're still deviating because their temperatures are so much smaller. So you want to have a good combo of both. So if I were to have you pick at which temperature and pressure would helium gas deviate from ideal behavior, so deviate's going to mean to be least ideal, like not as good. Which of these sets of conditions is the least ideal? Well, if you know what most ideal is, least ideal is just the opposite. So most ideal is when you're not under a lot of pressure, when you're not under a lot of pressure and you're nice and warm, cozy, high temperatures, okay? So least ideal is too much pressure and freezing, cold, not enough temperature. So that's going to be B. Low temperature, high pressure is least ideal relative to the other two. Okay? So now let's read this one. Which of the following deviates least from ideal behavior? If it doesn't deviate a lot from ideal, it is more ideal. So which one of these is the most ideal? And now this is not based on pressure or temperature. This is solely based on identity. And so we're going to pick, yes, good job, Brian, argon, because it's a noble gas. Noble gases and diatomics tend to be more ideal than any other gases. Okay, so now I throw this one at you, and I have not taught this yet. I go, okay, which gas deviates least from ideal behavior? And now again, this is based on identity and not pressure or temperature, except I did something mean and I gave you all noble gases and all diatomics. So deviating the least would be the most ideal. Most ideal. Anybody want to take a guess at who you think? I don't expect you to know, but who you think and why you might think that? I feel like the most common guess and what I guessed when I was younger was noble gases, because you hear the word noble and they just seem to be like they should be the most ideal because they're noble and stable and everything. And it's not going to be noble gases. And it's not necessarily that it's not noble gases, it's just not based on that. It is hydrogen. And yes, you, Kevin and Brian, you got it right. And it's because it's the lightest. It's because of molar mass. It is the lightest. So if you had noble gases, it could be a noble gas if the noble gas was the lightest. So the lighter ones move the quickest, okay? They will be least affected by all of those condition changes. So the lighter one wins, okay? It's the most ideal if you had to pick between all ideal gases. Any questions on that? Okay, gases multiple choice question. So a rigid 10-liter container. So rigid means the volume is not allowed to change. Holds water vapor at a temperature very close to water's boiling point. So some of it's turning into gas at this point. Remember, it's turning into gas right now too, even at room temperature, just not a lot. The measured pressure, though, is smaller than the pressure that you would have predicted using Pervner. So like they measure the pressure, so that's your experimental, and then they did their calculation in Pervner for their theoretical, and they realized that the pressure that they're measuring in the lab is coming out too small. So what would be a reason that the pressure is lower than it should be? So let's look at A. Water molecules break into hydrogen and oxygen molecules. So this is possible. If you heat it up enough, this is possible. Now, let's balance this. If you go from 2 moles of gas to 2 plus 1, 3 moles of gas, more gas means more pressure. You would have an experimentally high pressure. So this is out. Okay, the next one says water molecules are very attracted to one another. This is true, they're polar, okay, causing the molecules to hit the walls of the container less often and with less force. So this is the answer. I'll talk about why the other ones are not the answer. Obviously, if I tell you B is the answer, D can't be an option, and we'll talk about C in a minute. So water molecules, what they do, and this is going to make even more sense when we actually get to this chapter of intermolecular forces, is they're very attracted to each other because they're very polar. So if I have this container, right, and I have water molecules zipping around in here, well, if they like each other, instead of this water molecule zipping past and hitting the wall, okay, it's being attracted to this guy and they're interacting with each other, meaning it doesn't hit the wall as often, okay? Now, if it doesn't hit the wall as often, the pressure is going to be lower because instead of them zipping and hitting the walls, they're doing this instead, and they're not just flying past each other, okay? So the attraction of the water molecules is what causes this. So B is the answer. But let's talk about C. It says the volume of the water molecules is too large of a fraction of the volume of the container to be considered negligible. Oh no, if water molecules were huge in the container, as opposed to really, really small, if their volume wasn't negligible, this would create more pressure, right? Because now the size of the container is becoming relevant, and so are the water molecules. So this would cause an increase in pressure if the water molecules were now really, really big relative to the container. Okay, so that's why that one is out. Any questions? Okay, everybody take a deep breath. Do not freak out. This problem is not hard in the sense that it's plug and chug. It's only hard because there's a lot of stuff going on. So we're going to do it piece by piece. Here's the deal. This whole entire chapter, we have been afforded the luxury to follow the kinetic molecular theory and use the ideal gas law that follows all of the stipulations of that theory. And it allows us to easily calculate pressure or volume or T or moles if we know all of the other ones, okay? Now, in real life, gases don't actually follow ideal behavior, okay? They behave like real gases. If I were to ask you, which I'm about to calculate like pressure or volume or temperature of a real gas that does not follow the ideal gas law, this is the equation you would have to use. It's called the van der Waals equation. It's gnarly. And it's not gnarly in the sense that, like I said, it's plug and chug really, but it's just a lot of stuff going on and it takes forever. So we're going to do it. So look at PV equals nRT. And then these adjust for the fact that it's not an ideal gas. Now, again, P is pressure, V is volume, N is moles, R is the gas law constant, T is temperature in Kelvin, and then these little guys are constants that would be given. You don't have to know them. They were determined experimentally, okay? But they're given, and they're specific to each individual gas. So like oxygen gases, A and Bs, are not the same as helium gases, A and Bs. And helium gases, A and Bs, are not the same as carbon dioxide gases, or A and B gases. So if you look at this problem, it says calculate the pressure in atmospheres. so I want it to be ATM, and I give you how many moles of nitrogen, and I give you a 10-liter container, and I give you temperature, and I give you those little A constant and B constant that are specific to nitrogen gas. Where did I get them? I looked them up. So I looked them up. You wouldn't like memorize them or anything. So we're going to use the van der Waals equation. Everybody breathe. Okay. So what I highly recommend is doing this one piece at a time. So P plus A N squared over V squared times V minus N times B equals NRT. Okay, so let's plug in. I'm going to do this the opposite of I did in the other class. Let's plug in the N, the R, and the T. We already have all these numbers, right? N is moles, it's 0.5. R is a gas law constant. We're going to use the 0.08206 because I asked you to calculate the pressure in atmospheres. And T is temperature in Kelvin. Like this side is plug and chug. So let's do it. 0.5 moles. And I know it's 4 sig figs, okay? 0.08206 liter atmosphere over mole Kelvin. R is the gas law constant. T is temperature in Kelvin. So 25 Celsius right here is 298 Kelvin. Now I'm going to show you units. The units will be funky until the very end. Moles cancel, Kelvin cancel, and we're left with liters times atmospheres. I am going to wait until you guys give me this number, please. You guys need to calculate this. You aren't just going to leave me to do it. 12.22694, right? And then the units are liters times atmospheres. Okay, so I just did this whole thing right here. That goes on that side. Okay, over here. So we're solving for pressure. That's this guy right here. So I have pressure plus, let's just do this term. Let's just do this term and we'll write it in there. So A is right here. It's this constant. So 1.39 atmospheres times liters squared over mole squared. Okay, that's just A. Multiplied by N. N is moles. That's 0.5 squared, right? Oops, I want to write the units. A times N divided by volume squared. Well, the volume is a 10-liter container. And that's going to be squared. So that's going to be 100 on the bottom, right? So look at the units. Liters squared will cancel. The liters squared will cancel. And this is going to be moles squared. So the moles squared cancel. And we're left with atmospheres, which is a pressure unit. I will wait for this one also. So this is P plus, this one's a small number if I'm not mistaken. 0.003475, that sounds familiar. 0.003475 atmospheres. So I've just taken care of this term. Times volume is 10 liters minus the moles times B. Now that's its own little term. So the moles is 0.5. I know it's a bunch more sig figs. Times the B constant, which is given, 0.0391 liter, over moles. So look at the moles cancel, and you're left with liters, right? Because liters minus liters is going to make sense. So 10 minus this number is, I think it's 9.98, if anybody has it. Okay, so 9.98 liters. That's this term right here. So all this equals 12.22694 liters times atmospheres. So this and this equals this. So what do? You divide both sides by 9.98 liters. Okay. That gets rid of my liters. And now I'm left with atmospheres. And then what you have is, sorry, I'm gonna have to erase up here. Where should I erase? So now we have P plus 0.003475 atmospheres equals, what's that number, 12.2 whatever, divided by 9.98. Anybody have that number? $12.22694 divided by 9.98 is 1.225 something 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 atmospheres. So you just subtract this number from both sides. Okay. And you get one, let's do 4 sig figs, 1.222 atmospheres of pressure using the van der Waals equation. Oh my gosh, that took forever. Like forever, right? So this equation is so tedious. So the whole reason I made you do this is because the kinetic molecular theory allows us to use the ideal gas law. We have to kind of pretend some of certain things aren't true, but it's like, oh my gosh, it's better than doing all this work. So let's calculate what the pressure would have been if I let you use Pervner instead of van der Waals. Well, Pervner is a much easier equation. PV equals nRT. Sorry, I'm going to get rid of all this. PV equals nRT. Rearranged, P equals nRT over V. What's the moles? 0.5, right? I know it's more sig figs, but you know. R is 0.08. It's the gas law constant. Ugh. I swear, around this time in this period, my pen always starts to do this weird stuff. 0.0 0.08206 liter times atmosphere, right? That's R. It's the R gas law constant, mole, Kelvin. T is temperature in Kelvin, which is 298, 25 Celsius. All over volume, which was 10 liters. So liters cancel, moles cancel, Kelvin cancel, and you're left with atmosphere. So 0.5 times 0.0826 times 298 divided by 10. What'd you guys get? $1.223. Holy smokes. This is what it really would be, and this is what the ideal gas law gives us. So the whole point is the ideal gas law, even though we have to make some assumptions, still does a really, really, really good job of getting us pretty darn close to what the right pressure is. Okay, so we're not going to use van der Waals. Like the ideal gas law does a fairly decent job of getting us close to what the true real life number would be. And again, this would be most ideal under low pressures, okay, and high temperatures. But still, I would much rather use perv-nert than this guy any day, right? This took forever to calculate pressure. So we're going to follow the kinetic molecular theory, and we're just going to appreciate perv-nert more than we did before. Any questions?